Let's have a look at the reduction formula, which is expressed as I subscript n and can be found by using the integral of parts. So let's say we have a function defined as x raised by n multiplied by e raised by x, and we want to find the antiderivative of this function. And to start solving the reduction formula, we need to apply integration by parts for this formula. So we can find our u, du, v, and dv, where we define our u to be x raised by n, and we can define our dv to be e raised by x. And now that we have u and dv, we are able to find du and v, where du is the derivative of u, which is equal to n multiplied by x raised by n minus 1. And when we take the integral of dv, we find that v remains the same, which is e raised by x. Now that we have all our parameters for our formula for integration by parts, we can substitute our parameters into our formula. And so we can write our first equation as x raised by n multiplied by e raised by x minus the integral of e raised by x multiplied by n x raised by n minus 1 with the integral with respect to x. And since n is a constant, we can factor it out. So our equation now becomes like this. Notice when we observe our new equation and we look specifically at this term, we see that it looks very similar to our original equation. Now this is where the reduction formula comes to use. And we can notice that the only difference between our original equation and our second term for our equation is that there's a -1. And this means that we can now write the reduction formula for this example as I subscript n is equal to x raised by n multiplied by e raised by x minus n multiplied by I subscript n minus 1. And there we have the reduction formula for example 1. Now let's try another example. Let's say we want to find the reduction formula of an integral from 0 to pi, where we have the function x raised by n multiplied by cos containing x, and we take the integral with respect to x. Then we can start applying integration by parts by defining u, du, v, and dv. And we can now let our u to be x raised by n, and dv be cos containing x. Then we can simplify du by taking the differential of u, which would be n multiplied by x raised by n minus 1. And v would be the integral of dv, which would then be sine containing x. We can now express these parameters in the form of integration by parts, where we have x raised by n multiplied by sine containing x, which are from points 0 to pi, minus the integral of 0 to pi, where we can write v and du, which is sine containing x, multiplied by n multiplied by x raised by n minus 1, where we take the integral of x. Now when we try to evaluate our first term, we see whenever x is pi or 0 for sine, then the answer remains 0. So we are then left with the negative integral from 0 to pi, where we have sine containing x multiplied by n multiplied by x raised by n minus 1, where we take the integral with respect to x. Notice that we can apply integration by parts again, where we can define u as x raised by n minus 1 and dv to be sine containing x. And then du is simply the differential of u, where we have n minus 1 in brackets multiplied by x raised by n minus 2. And v is the integral of dv. So the answer would be negative cos containing x. Now that we have all the parameters for this equation, we can write it in the form of integration by parts, where we have x raised by n minus 1 multiplied by negative cos containing x. And we take it from point 0 to pi. We can then multiply the negatives, and we see that we have plus the integral from 0 to pi, where we have our v to be negative cos, and we already multiplied the negative, so it's cos containing x, and we have our du to be n minus 1 multiplied by x raised by n minus 2, and we take the integral with respect to x. We can now start to evaluate our equation, where the first term for x would be pi, so it's pi raised by n minus 1, and when cos contains pi, the answer is negative 1. Negative 1 multiplied by negative is 1, so we can then plus the second part, where we have x to be 0, and since x is 0, the answer remains 0, so we can carry on to our second term, where we can now extract the constants within the integral. So we now have in brackets n minus 1 multiplied with the integral from 0 to pi, where we have x raised by n minus 2 multiplied by cos containing x, where we take the integral with respect to x. Wait, what do we have here? It seems that our second term in our new equation is very similar to our original equation. This means we can now apply reduction formula, which can then be written as pi raised by n minus 1 plus in brackets n minus 1 multiplied by the reduction formula, which is I subscript n minus 2. And that concludes the reduction formula for the second example.